And so what you're going to see is an expression with a radical in the denominator. And to rationalize it means they don't want a radical in the denominator. So if you rationalize the denominator, you make the denominator just a real number. If they ask you to rationalize the numerator, you would make the numerator a real number. But the trick is you have to write an equivalent fraction. So it needs to be proportional. It will be different numbers, but it will be the same proportion. So if I have 7 over radical 2, I need to figure out an proportional fraction that does not have radical 2 in the bottom. So here's the trick. You know you can do whatever you want as long as you do the same thing to the top and the bottom, right? So I need to make this a perfect square because it's the square root. So if I times it by itself, it will be a perfect square. And the rule is anything you do to the bottom, you have to do to the top. Because then you're just multiplying by 1, aren't you? And you're not changing your fraction. Now what I would do is in your notes, if you don't have multicolor, put that in a box so you remember that you're inserting it into the problem. You're multiplying by root 2. So on the top then, I would have 7 times radical 2. And on the bottom, I would have radical 2 times radical 2, which is radical 4, which is just 2, a perfect square. So we have just rationalized the denominator. This and this are proportional. They're equivalent fractions. But, of course, let's try this one. What if I want you to rationalize the cube root of 2 over 25? Now we know you don't have to write this step, but just so you're all clear, that is the same as this, right? We know those are equivalent. And this might help you too. You know that 5 times, or 25 is 5. Perfect cube, you know you need 3 of them. Because that does not give me a perfect cube. If I go 25 times 25, I think that's 625, and that is not a perfect cube. But if I times by just, let me get my red pen, root 5, or cube root 5, and of course anything you do to the bottom, you have to do the top, times cube root 5, so I'll stick that in a box because we're inserting it into our problem, and it's legal because you're just multiplying by 1. Then on the top you have the cube root, and 2 times 5 is 10. And on the bottom you have the cube root of 5 times 5 times 5, which we know is 125, or the cube root of 125, or 3 5s, is just 5, isn't it? I can take 3 of them out. So I still have the cube root of 10 on top, but I have just 5 on the bottom. Let's try one with a variable. Let's say they give you 5m over 11n. Now we're back to a square root, so I just need 2 of them like we did up here. So all I have to do is multiply by itself. The square roots are kind of easy. If it's a cube root, you need 3 of them. If it's a 4th root, you need 4 of them. But square roots are easy. We just need, so all I ever have to do is multiply by itself, because then I'll have a perfect square. But don't think you can do that if you're multiplying, if you have cube roots or 4th roots. Alright, so now, can you tell that's red? I'll turn another lamp, hopefully you can tell. Now, multiplying on the top, I have the square root of 55, and I have mn, right? And that's all in the radical. On the bottom, I have the square root of 11 times 11, which I could write as 11 squared, or I could write as 2 11s, like I wrote 3 5s, or I could write it as 121 n squared, however you like to think of it. Because no matter what way you write it, as 2 11s or as 11 squared, the square and the square root would cancel. The square root of 121 is 11. The square root of n squared is n. We know we've practiced variables, right? But the top is as simplified as it can go. So it's just stuck in the radical. And that's okay, because we're just supposed to rationalize the denominator. Now, believe it or not, the next step I think is easier, and for some reason it's always the one you'll see on tests. Maybe not the next chapter test, but on the final exam, this is the kind of problem they like. Where now I have a radical in the denominator, but I also have a plus or minus with a radical. Well, look what happens if I multiply by it's called the conjugate. The conjugate of 2 root 5 plus 1 is 2 root 5 subtract 1. So the same numbers, but a different sign in the middle. And you've probably, well, I know you've seen what that does, but I will remind you, we'll see it in a second. In a box, so I remember that I'm multiplying by it. I'm manipulating my problem. So, on the top, I distribute 3. So it goes times this and times this. Now, 3 and 2 are outside of the radical, so they multiply root 5. 3 times negative 1 is negative 3. Now, here's the fun part. On the bottom, look what happens. If I go first times the first, I get 2 times 2 is 5 times root 5 is 25. So I have 25. If I do outside times the outside, I get negative 2 root 5. If I do inside times the inside, I get positive 2 root 5. And if I do my last times my last, I get minus 1. Well, look what we have. What happens to the outside and inside? And that always happens when you multiply something by its conjugate. That's what's so great about a plus and a minus. The outside and inside always cancel. So they're gone. And look, I have a perfect square. So I just have 4 times the square root of 25, which is 5, which is 20. Subtract that 1. My top doesn't change, but on the bottom, all I have is 19. So believe it or not, this and this are proportional. They are equivalent fractions. Let's try one more of those, because that's the kind you're likely to see on your final. You've got to be good at them. When you see them on your homework, practice and practice them. Say, give me another problem. Do several of them. So, for example, and I think they're easier because you don't have to think. Like up here, you have to think, what do I do to make a perfect cube? What do I do to make a perfect square? But here, you don't have to think. All you have to do every single time is multiply by the conjugate. Just don't forget what a conjugate is. The same numbers, but different signs. And anything you do to the bottom, you have to do to the top. So we're going to multiply by that, which we know anything over itself is 1. So I'm just multiplying by 1. I'm not changing my fraction. Alright, now we have to FOIL both the top and the bottom. So lots of work. Here we go. First times the first. They're both in square roots, so I just multiply them together. Out, so I just multiply 5 times 2. Inside times the inside. Now 1's in a square root and 1 is not. So I just say 3 times root 3. And last times the last. Again, 1's in and 1 is not. So I just write it like that. Now looking at those, there's nothing you can simplify and there's nothing you can combine because every radicand is different. So you have that whole monster of 4, 3, so we get the square root of 9. And you could skip it, but I'll write it one more time. If I do outside times the outside, 3 times 2. Inside times the inside, I have negative. And again, 2 times 3, so I have 6. And last times the last, negative root 4. So, as we expected, the whole point of our choosing this conjugate was because the outside and the inside cancel. And this makes a perfect square, and this makes a perfect square. So, I have this whole giant thing all over 1, which means you could not write it at all. Just, you could write those. So, good luck rationalizing denominators. I kind of like this section. It's nice and short and doable, but it will absolutely see it on tests, so make sure you can do it.